Assuming that you see my screen, I want to thank you and the speakers before me for their presentations. My presentation is called Brains for Buildings, where to find all the relevant smart building data. I am very thankful of being able to present in this seminar, in this webinar, because I'm not the guy who is doing ventilation all the time. Let's say my background is mostly in semantic web technologies and building information modeling techniques, but I'm really glad to be able to present here as part of the webinar. I call the presentation Brains for Buildings because that's a project that we will be starting in the Netherlands on 1st of May, so not even started yet, but already presenting. And it's together with a number of partners in the Netherlands, including also TNO, the first speaker. So who am I? My name is Pieter. I have background in Ghent University, but I'm now working at the Eindhoven since 2019. And I also include slide 2 because I have been affiliated with Building Smart and the World Wide Web Consortium, trying to make standards regarding the information modeling and information management of building data. Worthwhile to say as well is that my background, I am now active in the Annex 81, which is not 86, but 81, which is about the data handling itself for the same purpose. So I have 3 parts of my presentation. First of all, the Brains for Buildings project, the why and what we would like to achieve. Second, I would like to talk a bit about the building data semantics, including BIM data, IFC, link building data, brick perhaps, and then the last part of the presentation would be about system integration, aiming for scalability and feasibility. So as you will notice, I will be talking a bit less about the sensor data, so I'm a bit complementary to the previous 2 speakers. Brains for Buildings, what is our purpose? We are aiming at buildings that are aiming to serve people's needs, in which building operation is key, and we would like to allow operational data and data analytics such as machine learning and AI, aiming to basically understand how a building is functioning and then to steer and control optimally. As I said, this is not only TU Eindhoven, it's together with TU Delft, TNO, and a whole range of other partners in the Netherlands. I will not do the entire presentation about this project, but I would like to give you the outset of why I'm here in any case. So we are trying to focus on a couple of end aims and end user stories. Fault detection is in there, user-centered systems in there, and flexible energy use. And my role, or our role in STE, a part of the role is to serve on the red part of the slide, which is data integration, trying to provide the data and integrate it so it can be used for the purposes on the left. So this is on the left, you see a screenshot of the structure. So we are here, and what we always have with this data integration part is that we always are supposed to serve the data for everybody based on coming from existing buildings, including field labs. Our targets are basically to aim for data connectivity, how to combine the data sets, how can we ensure security, ethical use, and privacy of data. Can we standardize? Do we standardize? To what level? How? And then aiming for system integration at an API level. I will return to that last part in the rest of the presentation. So basically, I give here also a project that we did before. It was in Denmark, where we looked at an existing stadium. That those are running tracks and swimming pools. Where we have a whole number of sensor nodes, and we have these dashboards which we have already seen, and they have a diversity in quality, but they always have data coming in, streaming in, and the best that we can get of the actual building is often a 2D floor plan or a zone model. Sometimes, in many cases, it's enough, but there's actually a lot more data that is available about our building, which could explain also some of the findings of the data analysis. So that's why I try to work on this, and I'm coming into this from the building data semantics side. So I will give you a brief overview on this topic. And I imagine that this is new for many people, so I will have a very light introduction, yet I will go forward as well. So in the World Wide Web, there's this initiative of linked data, and you can see here the slide and the website. And the aim of this initiative is to make 5-star open data available. I am now not saying that all our data should always be open, but in any case, what we should aim is at improved structured data that we have available online, which we can use. So instead of you gain basically a star per level, you gain a star for setting a PDF online, Excel online, CSV online, RDF, and then linked open data. When you link all the data together across different servers of data. You can see also that it also allows just structured data such as CSV, making them available as structured as possible. That's the idea. This is a rather old idea already. If you apply it to buildings, we would ideally come to a graph or a cloud of linked building data in which your building data is all connected to each other. So for example, in this case, you see database interface of one building, including the stories, including the walls, windows, and the interfaces between spaces, for example. And all these nodes clearly also have properties that you can request. That's just a starting point. So that's your linked data. You can basically link all data together using web technologies. That's rather feasible. Yet we do have a whole bunch of data available, all sorts of data available. We have already seen a bit, namely the sensor data, but we also have those geospatial data, the people going through the building. We have the BIM models in different aspect models, and we have 2D floor plans, and then geospatial data I already mentioned, and different kinds of geometry, such as point clouds and meshes. So we have a whole scala of options. And the question is, how can you make it available at a reasonable level so that you can reuse it? I'm not saying that we should always reuse all of this data, but at least we should have some opportunity to combine our data efficiently. If you look at the BIM data and the data that we have already seen on this topic on BIM, we notice that we have it's kind of repetitive, but we need agreements. We have lots of tools used in the market. We need modeling guidelines. It's nice that we have an IFC standard and we have the information delivery specifications, but they need to be also implemented in practice. Otherwise, you can only get what you get. So, for example, how are we modeling the space boundaries of an area? If we don't define it, then it's up to the implementer to figure it out. Are we using generic models, or are we using wall, windows, objects, and so forth? This makes a difference for the parsing and for being able of automatically going from this drawing to this drawing. So this is really important, which is basically up to a market. Although we have these BIM models, on the one hand, we also have the IFC, the Industry Foundation classes, and I will just click this available. So IFC is available in a number of formats. So you have the traditional Express format, but you also have XML and then the RDF graph. So those are just available. And also in JSON, you can also get quite far. Yet, in case you want to use one of these, be aware that those formats are always depending on the starting point, which is an Express modeling language. So it also defines these languages. And what we noticed from the years of going through projects is that there's a number of good things about IFC, a number of difficult things about IFC. So usually it's pretty good in defining the overall building shape and topology. That's not a problem. So that works fine. 3D is there. Then the classification of elements is possible, but there's not that many classes natively available, and you can extend it with BSD classes and properties. But in practice, you can see that there's multiple other classes and properties which do not come from a standard, and that also makes it difficult to work with. Then the third bullet is it's not impossible, it's difficult to include sensor data in IFC, such as time series data. So you have to find a solution for this, and then you have these file formats. I also included 2 diagrams here. On the right, you can see the classification, the product classes which are available in IFC and which are fairly easy to use. But yeah, we need more than these classes, obviously. And then on the left, you can see a diagram of how, for example, a building is described in the site and how it's relating eventually to a number of properties, which is fairly complex if you're not aware of it. So that's one difficult part of IFC. maybe one last thing to say about this, what is also difficult is that it's available in step, which makes it less easy to use for common mortal programmers, which are more used to JSON-like languages. So therefore, we have started this link building data initiative in the W3C. That's a whole bunch of years ago, in which we try to make linked building data basically available online using the best practices of the web. And we also include how we can use it together with other specifications, such as other standards and separate initiatives, such as Haystack, Brick, Semantic Sensor Network, GeoSparkle, and so on. And this has by now evolved into a couple of results. So one of them is the building topology ontology, which, yeah, you don't need to know all of the details, but it basically is a limited set of classes, which is extensible and easy to combine with other ontologies and datasets, and it's comprehensible. So it allows you just to describe a building, and it stops at a limited zone part. So it stops at the element and zone, which does not mean that this is where that you need to stop. You can also basically extend it with your own taxonomies and properties and so forth to describe your building, basically from scratch or from a BIM model as you prefer. This hierarchy on the left of building, site, story, and spaces is inspired by IFC. That's one part of the bot of the link building data initiative. So that bot is one part. The idea, of course, is to combine it with other ontologies so that you can describe a full building in more detail. And one example is available here in this link, but there's also a publication from Georg Schneider available, which is about the modeler ontology modeling, in which you can define, you have specified ontologies which allow you to define property management, properties, geospatial data, sensor data, schema.org, geometry, and that's basically all separated but linked together, which makes it web scale, queryable, modeler, and you can link at instance level. So basically what you then end up with, if you look at an IFC perspective or a BIM perspective, is that you have your building topology defined here, zone, element, and then your site to space. You have also products, and then separate from it, you can define a number of classes, which can be standard or unstandard, such as Rex, Waterstaat, or Oxtra ontologies. Furthermore, you can link to geometry or geospatial data. Talk a bit more about that in a bit. These are reference ontologies, just in case you would like to know. Yeah, I'm kind of, due to the audience, I'm obliged to say something about Brick, HTAG, SAREF, and real estate core ontologies, which are ontologies that are typically emerging from the area of smart buildings. And that's, yeah, and I try to look at them as well. I try to also use them. And if I have to say something about them, then I find that they are usually relatively disconnected from our BIM area, which has its good sides and its bad sides. There's a big focus on systems, so that's a good match for us to be able to define our smart building. We need systems, operation, and control. And most often they stop at the sensor points and equipment types, which is in many cases good, but we would like to go further and also include the BIM data. And then this table that's on Brick schema, yeah, I just want to be aware of the bias in here. I mean, if you tick all the boxes for Brick, then of course, yeah, I'm not sure. I think those boxes are also very useful as well. So just be aware of what's inside. That being said, Brick can do a whole bunch. So it allows you to basically define different types, air handling unit, variable air volume box. You can define the properties, the rooms that are available for it, and then the sensor points. Skip this in favor of time. What I want to say this is that we can basically use these ontologies or schemas so that we can link them together also with the data that we have available in a link building data area. So there's nobody stopping anybody to link system data from Brick with the bot ontology that comes from BIM data, and then basically describe your building as you can see it here for one of our TU campus buildings. Okay, so that being said, and I can return to this later on, I would like to still have 5 minutes on the system integration part. So because it's all very nice that I've been saying link data, link data, link data, and semantics, but we have all kinds of other data, so such as sensor data, geometry data, and so forth, and they don't fit that well into a linked data environment or in a graph. So there's a couple of solutions to it that you can see in research initiatives, and I pinpoint two of them in the presentation. One of them is mapping everything into RDF, mapping everything into graphs. That's one option, so we can transform everything in there. There's a couple of pluses. The plus is that everything is in the same format and database, and you can do inference. The minus is that we have unfit storage, so all the sensor points, the IoT data don't really fit in that graph. You have a disconnect from origin often, and it's difficult to apply our machine learning algorithms, which we saw before in the other two speakers. And how to handle privacy and security, because most of the data is raw databases. So, but it's still an opportunity. So what you can then see is that we have a number of data formats, which you can see here on the left, native data formats, which we extract, transform, load into a larger RDF store, so linked data. Not necessarily open, but linked in any case. And then we can link this to other linked data, for example, governmental data or weather data, for example. And then your end user application, which are the applications you already saw, will basically use this data that's available in those stores. And then you can see a couple of examples that have been developed in the past. The downside of this, there's a couple of conflicts here, in the sense that our data here gets loaded, so we are disconnecting from our source, and our specialized software data is basically lost. The second conflict or difficulty is that we are managing our links in two places, namely in the backend of our application and also in the stores. The third one is our security and data access protocols. They need a layer in between. So what we typically try to aim at is a second approach, which is to maintain specialized data stores and deploy web technologies to combine them all, or what I briefly call system integration. The plus is that we have good data storage, data stays at the source. We can deploy those machine learning algorithms because the data is still in its sensor data formats. We can allow privacy security protocols. The minus is that we have a multitude of systems and we need expertise and software to handle them. That's a downside, of course. Then that would then lead to this diagram. I can brief, so it's kind of the same. We have a number of native formats in which we have native format data storing techniques. We have an API. We ensure the linking on this environment already without going all the way into RDF. We also allow other REST APIs on top of other data sets, and we make them available using standard web technologies to multiple end user applications. So that would basically allow us to use this data, but also the BIM data that we have in the semantic store. We'll go a bit faster here, because I notice we end up out of time. I just want to briefly mention that this is also on a project we can easily apply also for 3D geometry, which is very difficult to handle the point cloud data together with the matches of your column, for example. That we can basically also combine using the linked open data cloud, but still pointing to individual files or portions of files. This will be one of my last slides. So what we try to do is, for a physical building, what I propose is to basically enable a 3D BIM model, which we can make available using a knowledge graph or a graph database. We can use a MongoDB to store the 3D geometry. That's another topic. But apart from that, we try to also include our most common sensor data systems here available that lead to time series databases, and we try to combine these on the system level. And thus we allow security and good data integration. I will skip this, and I would like to just land on my takeaways slide. So my takeaways that I have, if I have to summarize this very briefly in a couple of points, what I would take away is structure your data as good as you can, and then furthermore make agreements about how you structure data. Just not just structuring is basically not enough. You have to communicate how you structure it. Be critical towards the acronyms and look beyond them. That would be nice. Store your data in dedicated technologies. Don't transform everything to the same, and try to aim for those that system integration. And I will hereby thank the audience for their interest and attention. And I will hand over to Mark as well.